So can I give you an idea about the solution of this stochastic differential equation? Well, actually, so if we take, so what is the solution of a stochastic differential equation of this type? Well, it turns out that we can find this solution, and it looks like it's the stock price today, a certain initial stock price, exponential, r minus sigma square over 2 t plus sigma wt. This equation satisfies this differential equation. So this equation, so we are able to find a function, a stock price, how the stock price behaves over time, according to the right-hand side. So this function solves this geometric Brownian motion. Well, to see this, it's not so obvious, actually, and the reason why it's not so obvious because it's a stochastic differential equation, so we have a Wiener process to handle, and therefore, to really prove this, we have to apply Ito's lemma again. So can I give you an idea how to show that this equation is really the solution of this stochastic differential equation? Well, suppose we start from here. First of all, let me divide on both sides the s. Though the s cancels here, but it pops up here. So what do I have then? I have on the left-hand side 1 over st dst is equal to r dt plus sigma dwt.
Just to verify, when we discussed Ito's lemma, so far we never really had st term inside. We only had drift and diffusion without st.
Wait a second, I tell you, you will see when Ito's lemma pops up, okay? Then maybe if there's a problem, you ask me again, okay? So here I just move the s on the other side, and then I have 1 over s dst r dt sigma dwt. Okay, that's simple algebra. And then let's say, why not integrating, from 0 to t, all these terms? Well, obviously, this is a normal Riemann integral, high school, for dt. So if you integrate this, you have r times my integration variable is now also dt. And Chris asked me, that's sometimes a little bit odd because the boundary is also t, and therefore sometimes I write here ds. Then the integration variable is s. Plotting in the boundaries, t and 0, you see t remains. So it's rt plus, well, what is this? Well, you can say the sigma is a constant, no problem. And if we integrate dwt, well, this is wt at the boundaries, t and 0. But w at 0 is 0, right? The Wiener process always starts in 0. Therefore, this is just w at t. And on the left-hand side, we still have this integral, which is, that is not so easy, because here actually you have, behind this dst, right, you have this whole equation, right? And therefore we cannot compute the left-hand side, but it seems to be that the left-hand side is equal to the right-hand side. That is what we see from the first step. And if you take a look, well, it turns out that here we have RT, this component, we have sigma WT, but we also have in the solution this term, which is not in here. And now I will apply e to its lemma, and you will see that then this term pops up. So how can I do this? Well, suppose we have a function. Let's call this function set. And this is dependent on my s and on my t. And now my guess, I make a guess and say, let's assume that this function is the log of the stock price. So this is what I assume, assume. So you assume there's a function, it's the log of the stock price. And now I apply e to its lemma. Now it will pop up here on the next side. I will apply e to its lemma, or formula, on this function set. And now take a look. Well, we know that this is, on the left-hand side, according to e to its lemma, we have d set. And then we have to compute the derivative in respect of t. Well, there is no t, right? There is no plus t or times t. So the first component is 0. Then we do the derivative in respect of s, our underlying. Well, the derivative of the log s is 1 over s. So it's 1 over st, it's the first derivative of this function, times the change, dst, according to e to its lemma. And then e to its lemma is telling us we have to take a look to this new term, which is a half, 1 over 2. The second derivative of my function set. What is the second derivative? This is the first derivative. The second is, well, there's a minus, comes in front, and then we have 1 over st squared, right? If we do once again the derivative of this 1 over s, we obtain minus 1 over s squared. And then we have to add, according to e to its lemma, the square of these two parameters. So sigma square, s square, and then it's not dw square, because dw square is, according to e to its lemma, dt. In this line, I applied e to its lemma for this function, for this guess function. No t component, first derivative of my s component, and then the second component. So, and now what I do next, well, let me substitute in for ds my stochastic differential equation, the right-hand side. And if I do this, well, I see there is this s here and this s here, and I have an s in the denominator, so this s cancels, and therefore what remains here is r dt plus sigma, right? This s and this s cancels, dwt. And then we have here plus and minus, which is a minus 1 over 2. This s squared and this s squared cancelled, so we have just sigma square dt, which is equal to the left-hand side, and this is my function set. Can I write for the function set my guess, which was the log of s? Take a brief look to this and compare it with my solution function. Can you already see that we are very close to r minus sigma square over 2, and both are dependent on t, the first term, and plus this sigma dependent on w. The only problem here is we have the differential. So now we have to go back. We have to integrate, right, to get this solution. So what I do here now again is I do the integration. Well, maybe I bring first these two terms together, but anyway, so I do integration from 0 to t, 0 to t. So what do we have? We have here r minus sigma square over 2. dt, I integrate over my t is my integration. That's a little bit odd once again. Let's say it's ds. So then we have s. When we do the integration, we substitute in the boundaries. Well, then it's t. For 0, this whole bracket is 0. So what remains? It's this bracket times t. Plus, here it's the same, right? We do the integration, which is sigma is a constant. We get this wt, boundaries, t and at 0, but at 0, my w is, my Brownian motion is always 0, though we have just the w at t is equal to what we have here on the left-hand side. But on the left-hand side, integration and differentiation cancels, and we just evaluate this function at the boundaries, which is, in the end, you can say ln st at my boundary, 0 and t, which can be explicit. That's the ln of st minus the ln at s0. So let me bring the ln s0 on the other side. Then we have this plus, can I write now this all in a bracket? Sigma square over 2 dt plus sigma wt bracket. And what I have left here is the logarithm of my stock price, st. And now we are very close to the solution. Why? Because here we have the log, and what I want to have is just the stock price, not the log of the stock price. So I have to do the reverse, and that is exponentiating. So using the exponential function, that gives me just here the exponent of ln s0 gives me the stock price at 0, and then this plus turns into here exponential of this, yeah, and the plus is then the multiplication. And in the exponent of the exponential, I have this term, r minus sigma square over 2 times t plus sigma times wt. And this is the solution I already mentioned in the beginning for this geometric Brownian motion. So here you can see why Ito's lemma is so important and why this solution is right. If we don't have stochastics, this term would never pop up. It would just be this and some term like this. But this is due to Ito's lemma, this term here. So this is just an illustration, okay? How to solve? Well, now you can say you have solved a stochastic differential equation. I promise you there are not many students and even professors here on the campus who did it